Hello everyone, welcome to the third tutorial of our course in cartography, uh, cartographic visualizations in GIS. So this is the third week and this tutorial will only be recorded. I'm in our notebook environment and I have already pulled the latest changes. So this week 3 has been added to my environment. If you haven't done it, now it's time to do it. And once you do it, you should have this new directory in which you have a bunch of folders and also notebook files as usual. So we are going to cover a number of topics this week. One of the things is non-cartographic representation of geospatial data. So this is a course in cartography, and no wonder we have focused on creating maps for the most of the course. But here in this part of this tutorial, we want to acknowledge that there are also non-cartographic ways of representing geospatial data. So although maps are usually deemed as the most powerful way of visualizing geospatial data, they're not only the only way. And sometimes with some data sets and depending on what you want to show from the data, some other methods might be worth considering. Uh, a few reasons why you may want to consider non-cartographic representations or visualization methods for your geospatial data. One can be for simplicity or simplifying the complexity. Well, they are sometimes simpler to create and they can help simplify very complex data sets. So if you have a data which might be very hard to uh, visualize using a map, or if you visualize it, it might become very complex and very hard to understand, and you think that you can visualize the same information using another method without use of map, then why not consider it? So it's one reason. Another reason is emphasizing connections. Uh, of course, maps are very good at visualizing special relationships, but sometimes if you really want to highlight certain connections, it can be special or something else, then you can consider other forms of visualizations. And then for facilitating comparisons, some visualizations can help it make easier to compare special relationships across regions or different kinds of categories. So, for example, if you have two charts side by side, it might be quite easy to compare depending on what you are visualizing. So these are a number of reasons why you may want to consider also non-cartographic solutions when visualizing your data. So in this lesson, in this tutorial, we will talk about this briefly. We will see a few examples of how this work and how this work and how we can implement them. So the first example is a network graph that we are going to use for visualizing relationships and adjacency there. These are particularly useful for showing this kind of relationships. There are advantages. There are good for identifying clusters. They can help you identify like central nodes based on the connectivity and where they're positioned on the graph. And they can show the relationships in a very intuitive, easy way. But there are also considerations. If you have a lot of nodes or edges in your graph, then it becomes very complicated and finding the right layout can become very tricky. So in this lesson, we are going to use the good old matplotlib, which helps us handle the visualization. And also we will use networkx. Those of you who have taken the AutoGIS course before, you might remember that we use this library to work with network analysis. Well, networks are also a form of graph, so it doesn't matter whether the network X helps you with work with graphs. So this graph can be road network like we did see in AutoGIS course, or in this case we are just using it to visualize adjacency relationship in a number of states in the United States. So we have an example of a very simple data, which is just typed in using in form of a dictionary, a Python dictionary. So we have the key of the dictionary is state, and then we have a list of other states which are neighbor to this state. So we have a simple data structure. Of course, in real cases, it's just for demonstration. In real cases, probably you have a data in table format. You have to do a bit of analysis and data processing to get it in a format such as this one so that you can easily create your visualization. So we start by importing the libraries we need and giving them a short name, PLT for matplotlib, and network X, we give it a short name NX, which are common names for these libraries. And then, yeah, this is our data set. The first thing we do in this working with this library is we create our graph object, and the syntax is quite simple. So from the library, we just access.graph, and it creates a graph object for us, which with the name G in our case. Then what we are doing is a for loop going through our data and creating our nodes and edges based on this data. And yeah, so then the next thing is to generate positions for each node. So the library helps us automatically create the layouts where things are positioned. Uh, so we are using this Spring layout, which is a layout optimization algorithm. You can read about it more, but it just somehow tries to optimize where things are placed. Um, yeah, so the output of this is random by providing a seed value which we are trying to make. We are making this reproducible. So every time we run this, we would get the same output, not randomly different. And then we create our plot. So this is a familiar syntax for us, like providing the size of the figure we want and the colors and then font sizes and again colors for the title and so on. So very simple, easy. And then we are drawing the nodes and edges and providing the position that we just calculated using this algorithm earlier and adjusting the transparency. Again, this is coming from matplotlib, so we should be familiar with this already. And then applying the labels, in our case, I'm using bold and making applying the dark gray color to it. I don't want the access, it wouldn't make any sense for a kind of graph, and then I'm using plt.show to make sure that the result appears here in Jupyter Notebook. And this is the output, so it just gives you a very easy understanding of what a state is neighbor to what, and for example, which states are a bit more central with more neighbors. So this is a useful visualization for this kind of data. Another non-cartographic visualization that can be used also for this, like similar relationships, uh, is a chord diagram. So a chord diagram provides, like, it shows connections, but it can also show the strength of the connection. For example, if you're visualizing the flow from point A to point B, this flow can be a migration, it can be uh, anything, and it can be any kind of mobility, for example. Then you can visualize the volume of that mobility easily. Uh, so there are advantages. So it looks nice. It allows you to also visualize the strength or volume of the flow if that's what you're visualizing, and they look appealing and engaging. But again, similar to the network graph we just saw, they can get, if there are too many connections, if there are too many entities, they can easily get crowded and overwhelming. So that's something to consider. So what we are working now for this visualization is an example data coming from Flickr nature visits by continent. So here we use the chord diagram to visualize the nature visits by continent based on the Flickr data. And for this, in addition to Matplotlib and Pandas libraries that we are familiar with, we are also using a specialized library that makes it very easy to create this kind of diagram. So here in the first cell, which we will just run, we import the library. So this is the library that we use for creating the chord diagram. And yeah, it is already installed in this environment. Then I'm going to read our data. So our data comes in CSV format and it is saved in this data directory. I'm going to run that. Let's take a quick look at our data, see what we have. This is our data. So we have rows with the name of the continents and the columns. So the names are matching. So the library knows that, okay, the, it should be matching. So it can figure out the connections. And also we have the volume of the visits, so which we will use for for our visualization. So what we are going to do next is to create a fake axis and subplots like we have done in Matplotlib before, and then we are reading the column names here, and then we are creating our diagram here. So this is how this library works, and you can check the documentation to see how it works, but it takes in our um, data as a NumPy array, and there is a function that can easily do this conversion for us, and then we provide the name of the columns and a bit of like a specifications. We can play with these things a bit to make sure our diagram looks nice enough. So let's just run this, and this is the output. So very easily we created a very well, decent looking chart showing us the flow from different continents in terms of nature visits. So yeah, so that was how we can create chord diagram in Python rather easily. So this was the practical part of this part of our tutorial, but one last thing I want to like highlight here is that, well, there are different kinds of non-cartographic ways of visualizing our data. We saw a few examples of them, and of course the more obvious example are charts. We are going to revisit charts and how to create interactive charts again next week. So, well, so now I don't open it up yet, but a combination of non-cartographic visualizations together with cartography, with maps, it can become potentially powerful. So here I have taken a picture, a map from this article, which I have linked here. And there they have very nice visualizations combining cartographic representations and non-cartographic representation, which becomes potentially powerful. Here they have also benefited from color coding to create connection between different images. So I advise you to check out this article and maybe you get ideas how to visualize things. Uh, yeah, so let's finish this part and continue with the next part of this tutorial. Okay, now we are going to use big data to create maps. If you are not already convinced that programming is a good skill to your set of skills as a cartographer for making maps, then this part of our tutorial might be actually, it might do the trick in motivating you to consider programming, in our case Python, uh, for cartography, especially if you're using with big data like the ones we are working today. You probably have had the experience of trying to import a very large data set into QGIS or other software you might be using, and you see it can get very slow. It might even sometimes crash, and you have limited control over how things work. But in a in the programming environment, you have more control over things. You can make processes more efficient, and if you use libraries that are, if you use good libraries, suitable libraries, you can do things very efficiently. So now we are going to work with big data. We have a few examples. The first one is a point data set from Flickr showing the points from 2019 to 2023, which has been retrieved from the platform's API. It is anonymized, doesn't have a lot of information except where the point is and the date when the photo was taken. Then we will work with origin destination line dataset of student mobilities to Germany. This is a bit larger dataset that you will later get to work with if you want in your final portfolio. But here we work with a simpler, smaller version of it, including only mobilities from other European countries to Germany. The original data is much larger. And then we will work with network speed, so speed test data from Ookla, a platform that you are probably familiar with. Many of us have used it to test our internet connection speed. And this is even a larger dataset compared to the two other examples we will work with here. And we will create a map. And along the way, we will learn a few techniques and tricks for visualizing large datasets. and we will learn some new libraries today. So let's start with Flickr data from Finland. So we have points in this data. The data is in this directory, data directory. We are just gonna importing using GeoPandas. We are not doing anything new here, doing a very quick plot, printing data head, and checking the number of rows in our data to just get some understanding of how the data is. Uh, this is larger than the data sets we have previously worked with, so it takes a little bit longer to import the data, but it shouldn't take too long. Uh, yeah, here's the output. So we see the data head, we have the geometries, which we have used to create the quick plot here, and also we have the column where we have the months the date when the photo was taken. And in the first step, I'm going to explore the temporal dimension of my data. I actually have the outputs. I will just clean the outputs. So we're going to start fresh. Uh, yeah, so in the first step, we already talked about the fact that, okay, not always you need a map, depending on what you are visualizing from your data. Sometimes some information can be effectively visualized non-cartographically. For example, I want to now quickly explore the temporal dimension of my data to see, for example, when do we have more posts and when do we have less? So seeing the fluctuation. And for that, I can just easily create a time series using Matplotlib and get an understanding of how uh, what are the changes. So for example, we see that we have a spike in number of photos posted around July 2020, and there are a lot of ups and downs. That gives you an idea how the temporal distribution of your data is. And this is Matplotlib, that's why the syntax is probably very familiar for you, and you can modify this plot the way you want. And of course here I have two important things here is to make sure that the column where you have your date is in datetime format, so Python can work with it easily. And then I'm grouping the data based on the date so that we can use it for visualization here. Of course, this is a good map, not map, good visualization showing you what data's temporal distribution is like, but we want to, of course, make maps here to also explore spatial distribution of our data. And for that, we are going to create a hex bin map. So the idea is to practice and learn a new technique for visualization. It can be used for any data set, and particularly they're useful for large data sets such as big data. So the idea is simple. It's basically a grid map, similar to what we did in week 2 when we were working with PPGIS data. The only exception here is that instead of using squares like we did last week, we are using hexagons to form our grid and do the calculation and then visualization. And there are a number of reasons why you see these maps, especially when working with big data. Well, one of the reasons is the visual appeal. They look nice. Of course, it's a matter of taste, but it can look nicer than grids. It is more efficient in coverage and there's less wastage. There is a reason why bees form their hives in hexagons and not squares or not circles for sure. And that's because they nicely fit and there's no space wasted in between them. Another reason is uniformity of data representation. Each hexagon has 6 sides of equal length, which results in a more uniform distance between the center of each hexagon and any point on its boundary. This uniformity ensures that each data point within a hexagon is equally representative of its center. This can be particularly important if you're doing some kind of proximity analysis, such as nearest neighbor analysis. Um, Another reason why these hex bins are common with data visualization, particularly with big data, is that they're computationally efficient. This might be a bit counterintuitive because they seem complex in shape compared to squares or circles. So you might think they're more complex, they're more computationally more complex, but algorithms for processing hexagonal grids are often more straightforward and computationally efficient for spatial data analysis. And that's, for example, compared to squares. And that's one of the reasons why they are used increasingly for big data visualization. For creating hexagons, luckily there is a library in Python, so we do not need to directly work with geometries, for instance. We can just use this library for creating hexagon grids based on our data. The library's name is H3. Unfortunately, we forgot to add it to our CSC environment, but there's an easy way of installing the library. So directly from Jupyter Lab, you can just put an exclamation mark, pip install H3 or Conda if you prefer to use that. I've done this already, so it's gonna tell me that it is installed, but if you haven't done it before, you can just install it. Of course, you can just do it from Python console as well, from the launcher. Yeah, so as we know, CSC, the data in CSC notebook is wiped out every time you open a new instance. So if you install this now, next time it won't be there. You have to do this again, but it's very quick. It takes like a second or two to install it. And once you do the installation, then you can import the library. And then I'm also importing Shapely, Polygon, and Matplotlib to create my map, and then map classify to do classification. And I'm importing the polygon twice, which is not needed, so I'm just gonna get rid of that line. I have manually entered the extents of Helsinki. First, we create our map for the whole Finland, so I'm going to comment out these two lines. For you, if you're doing this for the first time, it's already probably commented. What I'm doing is that first I'm finding a function using this H3 library that I imported, and it goes through every row of my data, reading the coordinates, and using the resolution we specify creates the hexagon grid. This number for resolution works decent for my extent, my scale of analysis and visualization, but of course, depending on what you're visualizing, you can try different numbers and see what works out best. So now I have my data, I apply this function that we just defined here, and then I do a bit of calculations, getting the number of points that fall within each of the grid cells, then creating the geometry and creating a geodata frame from that, and then visualizing. So let's just run this and get our map. I'm also applying classification. I'm using natural breaks with 5 as the number of classes, and applying color and adding a legend to the right lower corner. So this is my map. You can see the scale is not so good. I don't see any details, so I'm going to uncomment these 2 lines so we can focus our map on Helsinki area. So this is what it looks like. We have a bit of, we have a lot of red cells, probably, so the classification is not good. Probably we have to increase the number of classes or use a different classification method. But we are going to do that in the next step. And the coordinate system also is a bit off. So this is not a good map, and we didn't try to make a good map here. Even the axis is here and the ticks, which we don't need. But we are going to continue working with this and making the map a little bit better. If any of this is unclear, we have detailed description in this part, so you can check them out. And if there's something still unclear, you can just ask us. Now we are going to create an interactive map to explore this grid and this hex bin map we created a bit more interactively in a nicer way. For this, we are using Plotly. We are going to cover the topic of interactive maps next week, so you do not necessarily need to learn it now, and we are not covering the details. So we will revisit this next week, but we are just visualizing this hex bin map we created. Here using a corpus map, we are applying a classification, again natural breaks, this time with a higher number of classes to get more detail out of our map. And I'm using the column where I had the counts to do the visualization. Let's just run this and see what our output looks like. So here is our interactive output. So you can zoom in, zoom out, you have the legend, you have a number of other functions that come with Plotly. You can get a screenshot. Well, we will cover this next week, but yeah, so you can zoom into different areas and explore. Probably we still need even more classes to make this map look nicer, but of course you have a bit more variation in Helsinki area. We also have a tooltip, which is nice. You can see different values for different hexagons, and yeah, the map looks nicer than what we had before. Yeah, so that was a demonstration of how hexbin maps can be used for visualizing geospatial data and particularly larger data sets such as big data. Next, we are going to move on to the student mobility data. As I said, we have data set coming showing student mobilities from different European countries to Germany. So in the data we have lines. I don't have a visualization of it here, but you can just try to create the visualization quickly and see it is full of lines. Lines are overlapping. They're starting and ending from all over. So it is very crowded, very hard to use the map. So that's why I'm doing a bit of work here to make the map look nicer. So one thing I'm doing is that, well, first I'm reading the data, making sure that I only keep the data that is with a destination to Germany. And then I want to aggregate my data. So we have a lot of points coming from different cities, different areas, for example, in Finland to different parts of Germany. I don't need that amount of detail, and it's just gonna make my map crowded. What I want to visualize is that, okay, what is the volume of student mobilities from Finland as whole to Germany as whole. So I'm going to do aggregations. I aggregate the data per country using the origin country code. And then I'm also getting, I have downloaded European borders from an official European website, and I'm going to use that for my visualization as a base map, but I'm also using it for calculation in the next step, which I will explain briefly. But this will probably take a while, so I'm going to run it already while I'm talking. Yeah, so we do the calculations here. So in the next step, we are using the border. So I haven't added the visualization, but if you create a visualization of what we have at this stage after running the first cell, you will see that the points are like the lines from countries are starting at an like random location in the country, which doesn't look nice. So you want to make it a bit more systematic. So do you want the line to start from the country's capital? So to show the volume of mobility from Finland to Germany, do you want the line to start from Helsinki? Or it might even look nicer if you go with the centroid of the country. And that's what I'm going to do here. So I'm using this shape file I imported here, and I'm going to get the centroid of them. And I use the centroid as the beginning of my line. So I will relocate my lines to this new location. So I define a function for doing this relocation, and I apply this function. So I change the beginning point of my line. This way the map looks a little bit nicer. So I will run this cell. It is going to give me, it is giving me a warning about the coordinate system. Here the location doesn't really matter much because it's just centroid of the country for the sake of visualization. But of course, depending on what level of accuracy and precision you want, you may need to take this warning more seriously. In my case, I'm going to ignore that. Then I'm going to create my plot. So what I'm going to do in this step is, well, I visualize what we have, but also I want to apply, I want to visualize the volume of mobility. So the thicker the line between Germany and country X, the more volume of mobilities we have. And for that, I'm getting the counts and normalizing it and using it as my line width. So this way I'm visualizing, and I'm adding color, like I'm visualizing the lines up as blue, and also adding the Europe boundary to my map as gray, and adding applying a black outline to it. So this is going to take a bit of time because it's going through, we have a for loop here doing a lot of calculation, well, doing some calculation, so it takes a bit of time. But as you can see, I'm not using a base map here. I don't want to call base map a lazy solution, but it's not always the best solution. Uh, uh, it doesn't always, it sometimes serves a function, so it's good to use it, but the bad thing about them is that you don't have so much control over how they look, what is the amount of detail you have. But here I just want a simple map, not with any extra details, and I want to have control over how my base map in this case, like which is the polygons of the countries, look like. So I want to apply whatever color I want, whatever style. And that's why I'm using these polygons instead of a base map. Have a legend, you can probably improve the legend, just you can put real values. Here I just put low, medium, and high. And yeah, so there's room for improvement. You may want to get rid of these islands that belong to Europe but are not part of this part of the continent really. So there are things you can do, and since we are not using a base map, you can control what you want to visualize. So this looks quite nice, and the lines are starting from the centroid of countries. It can be problematic for some countries depending on their shape. For example, with Norway, the centroid is a bit off because of shape of Norway, or for the UK, it's a bit off. So for those countries, if you are publishing this map, you may want to like double check and manually fix those. Or for those countries, you may want to go with a manual centroid that visually looks nice, or the capital of the country. So before exporting, sharing your map, you should always double check and fix those tiny errors. So yeah, so that's our map of mobilities of students to Germany from different European countries. It's a nice looking map, and you can see that, okay, there are a lot of students coming from Turkey and from Spain, and like the thickness of line gives you a good idea. So if you compare these to the raw data that you can test and visualize, it is very crowded and unreadable. This is more informative and usable. Okay, next we are going to work with mapping with speed test data, and for that we are going to use a new library called Lunboard, which is efficient for working with large data set visualization. It's a new library, so there are things to be still improved. The documentation needs a bit more work, but the idea is to just showcase one new library here in Python that can work well and efficiently with big data. So I'm going to import a bunch of libraries that most of which we are familiar with. I'm particularly importing a color map that we are going to apply to our map. I'm importing Lumboard, Pandas, GeoPandas, and Pathlib. I'm fetching the data directly. I'm going to run this because it might take a while. So I'm getting the data directly from Okla, and it's in Parquet format. You might be familiar with this. It's a very efficient format. There's also GeoParquet format, and it's very efficient in size and also how in performance. Like for your exercise, I converted this data a data set like this to CSV, and the size was more than 10 times bigger when I converted to CSV. So it's very efficient. In this data set, we have the internet speeds from the first quarter of this year, 23, and we are going to use that for our visualization. We have information about internet speed. We are going to work with average downloaded speeds in kilobit per second. And yeah, so we download the data. We see we have over 3 million. We almost have 4 million points in our data. So it's a very large data set from all around the world. Creating a map is rather quick with Lombard. So what we are doing to do, we create a map instance first, and we create a map object, which I have named M here. Once you run this, it creates an interactive map for you. And after that, whatever change you make to the styling of your map is going to update that original object you had, map object you had created. So this is the output of our map. It looks quite decent already, but we are going to further improve it. You can see it's very efficient. You can zoom in, zoom out very quickly, very efficiently, considering how large the data is. This is quite impressive. And we are going to try and apply a field color. So I'm going to just apply blue to it. This is how easily you can just change the coloring style. But I'm going to make it a bit nicer. So I'm going to normalize the speed values and then use this to apply a color map. The color map that I imported already, which is like, I guess it's from like blue all the way through to green, through brown and yellow, a range of colors. So we are going to apply that, apply a bit of transparency, and we use this normalized downloaded split. So we get this nice gradual color change based on the actual normalized values. And I'm going to run this, and this is going to update how my map looks like. So now we got it. We got the new color style. One other thing we are going to do here is to change the size of the points so they're proportionate to the download speed. So I'm going to use this normalized download speed and multiply it by 200 to get the right size of circles for my map. And you can try different values to see which one looks better. And let's just run this. So the map is updated. Now we see the dots are a bit bigger, and we even have a tooltip showing download speed if you just stay over the points. So the download speed is visualized both using colors and the size of the circle. And this is very efficient considering how large the data is. So this is a very simple example of how you can use Lombard to visualize big geospatial data, and there are other libraries out there. You can try and see which one suits you best.
Okay, hi everyone. So I'm going to show you 2 tutorials for this week 3's QGIS exercises. So for Python, you look at a non-cartographic geographic visualization and dealing with big data, how to do that with Python. For QGIS, we're going to go a bit different way, not completely, but we're going to look at cartograms, and we're going to look at flow maps, or how to visualize mobilities. And to start off, as always, I recommend that you will go through the process of just opening CSC notebooks from here and launching an instance of the sort of environment, and then importing the GitHub repository, so you know the drill. Exactly the same thing that we've done for the previous 2 weeks. And this will get you the tutorial materials, the data, all the QGIS files that you will need to run and style these layers that we are gonna produce. So I won't do that now because I have them here locally, but as you do this on your own, so now is the good time to go through the process. and pause the video for a while, for example. But let's get to the materials. So first, cartograms. So you've probably seen a map like this quite a few times. It shows the results of, in this case, presidential election in the United States in 2012. And each county, so the local administrative level, has been colored by which candidate. In the case of US, there's usually 2 candidates, so that's easy to color by one of 2 colors. And then you can see the result here. So it's quite dominated by this red color, in this case signifying a Republican candidate, which we know in the end didn't win the election. So what's the problem here? So if someone who's unfamiliar with the topic or unfamiliar with the geography of United States, they might see this map and be like, oh, this guy that represents the red color is really sort of winning by a landslide. But the mistake there is assuming that this sort of dominant land or the color would also signify perhaps sort of success in the election, and that's easy sort of interpretation to make because the color is so dominant on the map. But we know that it actually both interplay of the sort of election districts or states in this case, I guess, but also the population of that area. So that's a more important feature than the land area of the region. So how do we represent something? Well, if we still want to sort of create a map, but not mislead or perhaps give a better interpretation to the reader, sort of the phenomena. Well, there's a long history of creating cartograms, which are mixtures of maps and diagrams, where we somehow, with some sort of algorithm, we distort the geographical space so that that area would represent some sort of value that we want to show on the map. Usually we will probably distort with population of those districts. And the benefit of a cartogram in comparison to, for example, just a diagram, for example, if we were to represent each county in this map with, I don't know, just like rectangles, so I don't like, we would separate from the geography, so then we would miss all that information, that so the pre-existing geographical information that the map reader will have. So we will lose all the benefits of the maps. We then have to explain a lot more about which county we are referring to, and so on. So in this tutorial, we'll use QGIS to create 2 maps, or rather we will use different methods to create cartograms in QGIS, and then discuss briefly what are cartograms through those maps, and how perhaps we can get you thinking of when you would like to create a map like this and when they're sort of useful. And some of the ideas in this tutorial are drawn from this article by Kenneth Field. And it's a really nice brief introduction to cartograms and has a lot of examples of cartograms of various types. So I recommend reading that if you're interested in the topic in general. But let's get to it. So launch QGIS as always, and prefer a recent one. It doesn't have to be this release candidate, just I think somewhere in the 320s, sort of somewhat relatively recent QGIS version. And for this tutorial, you will need 2 different. Actually, I'll move this. Okay, a few technical issues. So you will need 2 plugins. So one is called Cartogram 3, and both of these plugins are available in the repository. So Cartogram 3, which is a plugin for creating contiguous cartograms or anamorphic maps, created by Christoph Fink. And yeah, install it. Then another one, which is not strictly necessary, but we'll use it to create another type of maps, cartograms, so a non-contiguous cartogram. So it's called Shape Tools. It has a lot of nice features to sort of deal with creating these geodesic lines, for example, these great circle lines across the globe, and in many cases just like how to translate or transform these line features in many ways. So it's a nice like general plugin to have. Install that as well. So once you have both of these plugins installed, you can you won't have to download any separate data for this one, so you can just import the example dataset from Cartogram. So you should find it under vector and add sample dataset, and this will add to the project a population map of Austria in I think this population information is from 2017, and the population has been counted to these NUTS 2 regions. And if you're not too familiar with Austria, you can always add a background map just to sort of orient yourself a bit, like what's actually represented here. You don't need to add this by any means. And I guess one immediate interpretation here. So this plugin also adds an automatic styling that shows us the population density of these regions. So immediate thing you can see here is that the population density around the capital region of Vienna is way higher than any other region. It's not even close. So the population is highly sort of concentrated on the capital region, which is very common across various nations. So when there's major cities, of course, then population will be concentrated there. And usually these areas are then smaller, these administrative regions are smaller than perhaps the sort of less densely populated ones. And that creates problems if we again want to show some sort of phenomena on the map, like let's say now the election results, for example. So let's sort of deselect the background map and then start thinking what we want to do with this. So if you scroll down now to the section titled Non-contiguous cartogram. So first we'll look at the sort of very simple approach to creating these cartograms, where we just scale the geometries according to whatever scale value that we want to apply. So if for example now this geometry will be, we scale it like to 1/6 of what it was previously. Well, you see an example here. So for the non-contiguous cartograms, this is a starting position. We'll use this method introduced by Olsson in already about 50 years ago, and it's a nice paper. It has like descriptions of I can show it here, but it has descriptions of how to do this with pen and paper and the sort of scaling, physically scaling the features. So that's quite nice. But this is something that we can just implement with the field calculators that we have. So we can see the formula to calculate a scale factor, which we'll then use to scale each geometry. And that's the value, for example, a population divided by an area. So just population density, or density of whatever feature you want to represent. So in general, density. It doesn't have to be exactly square kilometers. It doesn't have to be population in general or whatever. And then take the square root of that value and then multiply it by the density of an anchor unit. And what's this anchor unit? It's one sort of special region that will keep the same size, and all of the other regions will be scaled relative to it. And for example, we'll use Vienna as our anchor unit because that's the one with the highest population, so the highest value. So Vienna will stay the same size, and all of these others will be scaled to be smaller because we want to represent sort of the accurately have the area represent the population, if you catch my meaning. So you've seen it in a while, and it's usually wise to have sort of an anchor unit that's high density. It doesn't have to be the highest density, but then that means that any areas that have higher density than the anchor unit will be scaled up. So we'll start adding field with the field calculator. So we can just do it, for example, here. And the population, calculate the population density squared. So we'll just start with the right side of the section of the formula, although we could do the whole thing at one time, but we'll split it up a bit, hopefully make it also a bit more easier to understand what's happening. So just as population density, these two fields, and you can see them, always check them out at the attribute table, and then we take the square root of them. Okay. And just to show you the attribute table, it's always a good idea to check it out. So the population, in this case, this layer has already a area calculated by square kilometers, but we can always also calculate it with the function. And then we have the population density squared. And population density squared is the highest for Vienna. Okay. Then we're moving on to the second. Oh no, it's not there. We'll move on to the second part of this function, so calculating the scaling factor. And just add another field. That's scaling factor. And again set it as a decimal number. And copy the expression. So we'll use the maximum of the population density squared to divide by 1, and then just multiply it with the value that we just calculated. And this part here is to calculate to get a sort of scaling factor for the anchor unit, and this maximum of population density squared is to get the value for Vienna. So it returns one value, and that's for Vienna. And then you can always get a preview of what's going to happen here at the bottom. So for Vienna, this scaling factor will be 1 because that its size will not be changed. And then for others, it's going to be about 1/10 of the scale that they were previously. Okay, now we have the values that we need, and we'll just scale all of these geometries with those scaling factors that we just calculated. And for that, we'll use the a function from the scale shape tools plugin that we just installed, and it's called geodesic transformations. Notice that there's also a default, or QGIS has by default these transformation tools, but they have a weakness about them that I don't like. So you could do a lot of different sort of transformations of these geometries. So rotate them, move them, whatever. We'll just scale them, and you could scale by a flat number, but we'll actually use a data-driven function to scale it by the scale factor that we just calculated for the field. So then it will apply the correct value to the correct geometry. So set the data-driven override, and with that you should have something like this. So it's not exactly sort of pleasant perhaps to look at, but it's an accurate representation of if you use Vienna as anchor value. So now all of these areas will have the same area relative to the population as Vienna has. So you can see that now we lost, for example, topological information, so we don't know the neighborhood, so the relations between these areas. It might be a bit tough to interpret if you don't know beforehand which areas are which, if you don't know the geography of Vienna. So you can check out the example map that was shown there, but it's probably a wise thing to in a case like this. Oh yeah, for some reason that one doesn't like to be duplicated, so we'll just add another sample dataset. So it might be wise to have some sort of background map that gives out the shape of Austria, something like this. Yeah. And as always, you can see example visualizations here. So in the plugin or in the tutorial notebook, and in this case, instead of having some sort of value to visualize these datasets with, these are just for demonstrating what is cartograms and how to create them. So these have just had a qualitative random color scheme applied to them, so you can see which areas correspond to which. So this approach for creating non-contiguous cartograms, it preserves the shape of the regions, but it also makes them quite small. You can probably improve this visualization by a few tricks, but it's still maybe not great for many purposes. You can consider using them, but you can probably see the weaknesses of this approach. Well, then there's another type of cartogram that we can easily make in QGIS, and that's called a contiguous cartogram. And this one will apply a bit more complicated algorithm that tries to preserve the shape of the regions while also keeping the topological relations intact. And for that, we'll use the cartogram tree plugin, and just run the plugin, compute cartogram, and be sure to apply it to this data. Actually, I rename this to separate it. So apply to this population layer and select population counts as the field to sort of to distort the geographic width. And these defaults are probably pretty well. You could reduce this max average error to a bit to make it more accurate, but I didn't see any significant differences. So you can also keep these defaults. And then it will calculate it, and by quite soon you'll have a map like this. And if we remove these background variables, or we can actually even keep that, so you can see that it's done its best to preserve the shape of these features, except for the area of Vienna, which, as we can see, has quite a lot of larger population density than the other regions. So then that's distorted to be representative of that fact. And again, there's an example here of which areas represent which. So this, I think, already looks quite a bit nicer than the contiguous cartogram one. But yeah, we've now created two types of cartograms. We could still have a short discussion of what we're actually now representing. And you could do this by following this field calculator instructions that I added here. So basically we'll calculate the proportion of population that each region holds. So for example, Vienna has about 21% of the whole population of Austria. And here are the expressions, how to calculate those in QGIS. I won't now run them because I have the results also here. And then calculate the area which each of the distorted, this area is distorted by the algorithm. So how much of land area of this whole now new geographical shape is represented by, for example, Vienna. And that's 19%, for example. So if you calculate these two factors here, you'll get an attribute table like this, roughly. And you see that these values are actually quite similar to one another. You might have some small differences, but I think probably the big picture will stay the same. So actually now that we scale with this population of the area, its land area will be quite similar to the population, because that's what we're doing. We're sort of distorting these shapes to represent a value. And it doesn't achieve like complete parity, because it has other objectives as well, but it reaches quite a nice balance where most of these sort of differences are within a few percentage points. So here's a quote that I liked, quoted from worldmapper.org, that has a lot of these cartograms. So you can check out the page, the examples here. So a lot of different variables and a lot of different cartograms. So from the frequently asked questions, so cartograms are best understood as pie charts, where the segment of the pie is reshaped to look like a country. So if we were to represent actually the population proportion in a pie chart, so we would have, in essence, quite a similar result as now doing with these cartograms. Except, of course, we will lose the geographical area, so we won't have the benefit of the maps that people recognize the shapes and where things are. So then we would have to add, for example, labels for each region, which gets very unwieldy once we have a lot of regions. But thinking of cartograms as similar to pie charts also helps to sort of figure out when they are useful and perhaps when not. So this is not part of the sort of tutorial that you can follow, but you can always create this map. So this map shows just the shape of Finland, and here it is distorted with this contiguous cartogram algorithm, and by the population of the municipalities. So there's about 300 of the municipalities, and these areas are distorted by the population of them. So now that we have so many regions, similarly to a pie chart, once we have a lot of sectors, so then the information content becomes quite tough to interpret, especially because the population between these regions varies so much. So do consider if cartograms are suitable for your use case. Maybe this type of map is useful for some purposes, but it also distorts the shape so much that can you really say that this is Finland if you see it just from the offhand. But if this sort of idea of cartograms emphasizes you, and I think they have very many good use cases, you can also look into approaches that are beyond the two approaches introduced here, ones that are, because I think those two are the ones that are easy to implement in QGIS with ready-made tools. You want to look at beyond QGIS. So then there are these cool graphical cartograms, for example, or gridded cartograms. And this article by Kenneth Field also has links to some links to tools that have implemented these cartograms. And I'm sure that there are also more like other tools to do this with. But that's something to consider if cartograms are your thing. And as always, you can run this whole process with a processing model, which you can find in the QGIS files. So you can download either the whole zip file or download just the processing model that's called cartogram model 3. So download it somewhere and then open it up. So I have it ready here. You probably have it in a download folder. So this runs through the whole process that we just went through and provide it with sort of population information and then run it. And you have these same results. And you can, of course, I recommend you to also think of how we would represent this in a layout, so how to lay out this type of data, which we now didn't go through in this tutorial, but you can see what I did, for example, on these example maps, which I'm sure you can improve on. So yes, that was how to create cartograms with QGIS. Okay, moving on to the second part of this QGIS tutorials. So we've been working with various sort of, I guess you could say the common thread now has been distortion of data somehow, or how to create a more effective visualization when there's sort of variables that might not be best represented by just raw geography. So for example, the non-cartographic visualization means, and then cartograms. And now we'll show another type of visualization method that is sort of similar to this. So edge bundling. So if you open up lines and edge bundling QGIS or whatever similar title it has in the end, so this other notebook, so you'll find this data type that's quite common, which is origin and destination connections, so line maps. And we worked with similar data before. So on week 2, we visualized connections between different airports. And if you check out the non-cartographic visualization notebook, so we'll also have some some origin destination data there. And by origin destination, just like we have two data points, and then we draw a line between them. So you can see an example here. I'm sure you've seen like similar maps in various occasions. And the problem perhaps with these type of maps is that they get crowded very easily. So once there's sort of not even that many visualizations and that many connections rather, so then we'll have with this mess that's called a hairball visualization by Porthus. And even if we were to able to make this a bit nicer, a bit like smart styling, we add some transparency and like, yeah, it still wouldn't be exactly a good visualization. So this line, this only has like some 400 lines, and all of them are heading to 3 regions in Germany. But we can't really tell much about the actual dynamics of what's happening here. So where do most people come from? And by the way, I'll explain the data in more detail soon. So where do these people come from? Where's the most visits, or where's the most exchange students coming from? We can't really tell, not too much about this. So in this tutorial we'll create a flow map that not only represents the connections between the places, but also the magnitude of them. So how many of some value are moving from one place to another. And we'll introduce 2 approaches to visualizing this sort of origin destination data in QGIS. This graduated line maps and edge bundling. So to start off, we'll need to fidget around a bit. So we'll need to download a plugin for doing the edge bundling. But sadly, this plugin is not publicly available in the it's not available in the official repository, so we can't install it from the usual route. Instead, in the QGIS files, you will find this zip file called processing edge bundling, which you should download. There should be probably a link to it as well somewhere here. Yeah, here. So download that link. And then, well, yeah, I'll highlight, for example, here. So download that zip file. Then you will have to navigate to start a new project in QGIS and navigate to manage and install plugins. So there's a separate path for installing these zip files, from zips. So actually I'll deinstall it or uninstall it. So that I can demonstrate it. So install from zip, and then there, and just install plugin. Yes, so now it's successfully installed. And remember that if you uninstall it, so then you'll need the zip file again to install it, so it's not in any sort of repository there. So then the data that we're working with has been prepared by Tuomas Väisänen and Oula Inkeroinen here at the Digital Geography Lab as part of the MobiTwin project, and it describes the student mobilities in the European Union's Erasmus program. And the whole dataset sort of in a raw format has been linked to here. But Tuomas and Oula have prepared the data to be sort of in a geographical format and easy to understand. And it shows where people originate from and where do they go to for like Erasmus exchanges at the level of the statistical NUTS2 regions. So it's quite rough. For example, in Germany, I don't know if there's a map for it here, but it's the second highest level in this statistical division. And as always, you should download these QGIS files if you haven't done it in previous set. So you can download the whole zip file that has all of them, like a folder, or then you can download the individual style files or the model file from here. So we'll start with something called a graduated line map. So if we want to represent the quantity of something, so naturally we can do it by just exaggerating the line widths. So if you want to say that there's 15 mobilities from one location to another, and then another location has one mobility to destination, so then we'll exaggerate the first one. And the data that we're using has been pre-processed quite a bit for clarity's sake, or have it a bit more brief, because these algorithms might take a while to calculate. So it only includes mobilities to 3 of the most visited NUTS areas in Germany, which are in Berlin, Köln and Cologne, then Oberbayern. Sorry if I now probably mispronounce those things. So you should start by adding the data to the project, which you can do, which you can download from here. So you need this Erasmus mobility data file. I should have it here. Yep. And in it you will find 2 layers, which is the actual mobilities, and then these centroids that we can basically just use for styling layers. And by the way, always notice the geographic reference system that's in use. So in this data, it uses this good Europe-wide coordinate reference system. And here's a QGIS tip, by the way. So if you ever need a quick, so the background map, a base map, you can always navigate to this coordinate section here and at the bottom, which is now showing for some reason on the capture. I need to make it a bit, it's annoying. Okay, for now it's showing. So this coordinate field here, so just type world to it and press enter, and ta-da, you'll have a world map. A simple sort of political world map with country borders. So you have the data, you can check it out a bit, see what's in there. And then what's in there is quite simple. So for the line connections, it's just the origin, code of the original region and code of the destination region, and then this combined field with both of them. And for these centroids, you will just find the name of the region, of the destination region for labeling purposes. So now that we have the data, we'll just use this aggregate tool that we used previously as well in the second week, and we'll group because you might notice that this data actually has just all the connections between regions, even if they are the sort of if there's 5 people going from this place to this place, so then there's separate lines, and we actually just want to calculate how many connections are between the places in total for our graduated map. So you can launch aggregate, and you will need just the field ID and the origin and destination ID. I think those are, you can also keep these ones, but you don't need them. You can remove them, and we'll group by this origin and destination ID. And then, because then we have groups of that are, for example, those 5 connections that I just showed in one group, and then we'll count how many unique values, how many unique lines are in that. And we'll name this one mobilities. And then for the origin and destination IDs, we can just take the first value, so it will keep, and it will keep the value that's in there somewhere in the connection, so we know which connection is which. And make sure you have this correct file selected, and then run it. And you will have an aggregated layer that looks physically the same as the another one. But if you now check it out, you'll see that these lines have the mobility connections calculated for them. And if you wonder why there are so few Erasmus connections, so this is actually just for the year 2018. I think it might be just for a few months. Yep. So that's the information that's useful for us. Because next we will want to start visualizing these connections. So we'll want to select graduated. Yep. And use these mobilities values that we just calculated. I guess there's, let's say, natural breaks. And now you can see that we styled them with color, which is, I guess, valid. You could do just that. Maybe add a bit wider lines, maybe not that wide. But actually, this is a poor example. But so now the sort of intensity of the color is representing the how many connections are between these places. But you would actually also wanna use size to implicate how many connections are between the places in addition to the color. And you can do that, but you can do by default both at the same time, which is a pity. And by the way, you can always sort of fiddle around. You don't have to follow what I've done with this styling. So for example, now I added 4 classes and this specific styling tool and this specific color. So do absolutely experiment with your own sort of approaches. So we wanna modify the size of the line connections as well as the color at the same time. So we can do that again with the data-driven overdrives. So if the width is now just a flat number 1, we can actually say that it should use the mobilities information to scale those values sort of flexibly. So I copied now this expression. So basically it says that use values from the field mobilities and scale them to a new value between 0.2 and 2.5 millimeters. So the lowest value will have 0.2 and the highest mobility value will have 2.5. And this tell it that we wanna get this like from minimum value of mobility, so 1 to the maximum value, which I think was 18. So scale all of those values, scale 18 to be 2.5. So instead of classifying the data sort of flexibly, we'll be using a flat value. We'll be using sort of a linear scale where we'll be applying all these values. So, okay. And now you can see that we have this nice exaggerated connection between this most visited places and well, places where most connections are from, and then de-emphasized a lot of these smaller ones. And then you could go on to do other style definitions. You could play around with transparency or opacity and colors. Now I don't think this one end of the sort of color scale doesn't really work well now because it's pure white. So even if we want to just keep this red color scheme, we could edit it a bit. So we could edit the color ramp to actually start from, I don't know, somewhere around there. So now we don't have those distracting pure white colors. So you could do this small tooling around with the values. And then, yeah, like I described this great sort of smooth ramp, this data-driven approach, as opposed to those, for example, for how many classes that we could use with the graduated style. And we can use now these line widths and line colors at the same time, which is a nice thing. But I think one weakness of this approach is that we don't have access to automatic legend. For example, I don't think legend represents this line widths, for example, smoothly. So that's a pity. And well, here's an example map of something I created with these styles. So I guess some things you can always apply these styles. So apply this to the line features and then use the centroids label to add these labels. If you wanna recreate this style. Okay, so we done graduated line maps. Now we will explore what if we don't want to show these sort of direct connections, these sort of origin and destination points only. We could apply edge bundling, which is a type of clustering algorithm for line features. So and it has been used a lot in sort of general information visualization, and we'll apply it to geographical data. And you can, if you want to read more, you can, for example, read this article by Anita Grace and others, or this article linked here. You want to sort of know more about the theoretical background between this, or about this. But yeah, we'll use this algorithm implemented by Grazer and co-authors and run this type of force-directed edge bundling, which is just one algorithm type of for doing this edge bundling. So it sort of connects lines that are going towards the same direction, are close to each other. So instead of having 10 lines going next to each other roughly to the same direction, it'll try to create one larger line that would be easier to sort of interpret what are those big mobility sort of trends. So you install the plugin from the zip file, so now you should have added to the processing toolbox a force-directed edge bundling algorithm. So run it on this 2000. Make sure that you have this original data selected. Then You can leave this cluster field deselected. It should make it a bit faster, but we don't use it for this now. Then this, in the notebook, you can see descriptions of these parameters, but for the initial step size, we'll go with 1000. So that's 1000 meters because it's in map units. Then we can leave this rest as they are. If you reduce them a bit, it should make it faster to run, at least these cycles and iterations, but then have a bit poorer result. And this should take about 1.5 minutes, so I'll pause the recording for that time and return to you once it's done. Okay, so now the algorithm has run its course. It took a bit less than a minute. So now we'll have the results. So if we started from something like this, so now a bunch of those connections have been bundled. So for example, the ones coming from Spain are now sort of heading, the ones for example heading towards Germany are sort of snapped together. And then in the notebook you'll find this description of these parameters, roughly what they do. And note that this edge bundle is quite sensitive to good parameter selection. So if you apply this algorithm to your own data, you probably have to fiddle around a bit and do it by trial and error to try to find something that works for your use case. And then there's a few examples here of what these, for example, how much this initial step size parameter affects the outlook of the map, so the end product. And in this style that you can get from here. So I have colored the connections by the destination value. And then you can see that if we, for example, go from 1000 to 10,000, so then for 10,000 these bundles of line connections are quite a bit more aggressive. So it creates a lot more larger sort of connections that zigzag a bit than the ones that have like a lower starting step value. And if you have the starting step value that's too low, then you will find little difference between the between just the raw values and the bundled output. So do select wisely. And then now that we process this map, so there's a description of sort of what I thought when I made this output map, which you can see if you scroll down a bit. So what was my thinking behind it and what elements I included, for example. So again, I relied on a dark map. I noticed I have a bit of a trend of doing that, so it probably would be good to be a bit more use a bit more varied set of visual communication tools, so maybe not rely on this dark map always, but I did it here. At least it creates this striking outlook. And then a quick title on this dead space that's dominating this top left corner of the map. Then using the world file with just the country borders as a background map to sort of orient the reader. And then data attribution information here. The other at the top bottom corner. The other features that you could add, maybe have some sort of information, for example, about not arrow if you like. Maybe it doesn't make sense here because people probably know how Europe is oriented. Or a scale bar. But yeah, Other things that I did, for example, is to add a high transparency value to the lines, exaggerating the line width a bit, just a flat number. So adding this transparency makes these bundles of lines more prominent, because if there's just a single line, so then it gets lost, but if there's multiple lines, so then they stack each other on top of each other, so then they'll be visible even if there is transparency. Yeah. And probably it's wise to now also play around with the, for example, the printout page. So now that we are representing the whole of Europe, at least in this example map that I created, so the output will be quite square. So remember to fit your sort of map to the location that you're representing. So next you can just consider in your mind, like, what do this, what does this map do well? Does it, in your opinion, represent these flows of people well? How would you do it differently? Or which do you prefer, this edge bundling approach or this graduated one? Or would you go beyond these geographic flow maps altogether? So if you're interested, for example, in this edge bundling, this is just a quick sample of what's possible, because sadly for QGIS that was the only algorithm that I could find that's the only place that has implemented this sort of algorithm in QGIS, and it's also really slow, sadly, so it doesn't scale well to a large data set. That's why we use this small one with just sort of one-way connections to the 3 places. If we were to use just, for example, even the whole data set for Germany, so then running this algorithm will probably take somewhere in the tens of minutes or 10 minutes. And if we were to run it for the whole of Europe, so then you'll be sitting by your computer even tomorrow, so it's going to take a long while. There are other implementations. If you look beyond QGIS, I've linked a few of them here. For example, this Python implementation, which isn't probably I don't think it's a library, but it's it should have some code to run, and it implements this that were presented in this paper, which is also shown in this demo. Shown in this demo that has, for example, this airlines dataset that we also worked with previously. So you can play around with these different parameters and see how this edge bundling algorithm deals with them. Or these migrations across the United States. You can bundle them. It should be, I think, relatively quick. I don't know if it actually does it in real time. If it does, it's quite impressive. And you can see how we get from this really a mess of connections to something that's at least a bit more readable. So if you're interested in edge bundling, it's probably wise to look at these tools that go beyond what's implemented in QGIS. There's also a link to a few tools for R, if you are familiar with that language. And as always, you can import the processing notebook, processing model. That's titled Lines Edge Bundling Model. And I won't show it now again, but just open it up in the processing notebook and then run it, and you should have these lines that are styled with the styles that I've used here. So that was it for QGIS tutorials this week. Keep up the good work. Remember that you can always use multiple tools. You don't have to stick with QGIS, just with QGIS or just with Python. You can use them both, or you can use other tools if you so wish. And now that we looked at some of the maps that you created in the first week, I've been at least really impressed, so keep up the good work.
Now let's briefly talk about your exercise. So this week exercise, the first part is the weekly reflection. So we had a lot of interesting things during the week. We had a guest lecture by Franz Mochnik, and then so we had a good lecture. We had also an interesting discussion in the afternoon of our Monday. And then, so write a bit of reflection, what you have learned from this week, and just a bit reflect on the week and the learnings, also the discussion we had in the afternoon. And then second part of your report is thinking beyond maps. So today during the tutorial, we briefly talked about how we can sometimes visualize geospatial data non-cartographically. So here I want you to use your imagination and come up with cases where it would be useful to use non-cartographic visualization to explore something about geospatial data. So try to be creative. You do not need to create a presentation, a visualization. You just explore the idea of think of some data or a certain aspect of a data which can be efficiently and nicely visualized without use of a map. Then we have the mapping part of the exercise where you get 6 points out of the 10 for the week's exercise. And you have 3 options to choose from. So first option is to create a hex bin map of big data. We already worked with the speed test from first quarter of 23. Now we are going to work with a similar period, but from year 2022. You can download the data directly using this link, either through Pandas, through your Python environment, or whatever programming language you're using, or download it directly from your browser. And then you can choose to go with Python or QGIS. If you want to work with CSV, you can run this piece of code, which uses Panda library to convert data from Parquet to CSV, and the data becomes very large. So if you have access to Python and you're comfortable enough with that, which I hope you are, then you can just run this code and do the conversion. But if for whatever reason you cannot do that yourself and you still want your data in CSV format, I also prepared a ready version for you, so you can just download it from this link here. During the tutorial, we learned how to create hex bin maps in Python. If you want to try this in QGIS, then there are a number of tools. So there is this QGIS tool that can create you different kinds of grids, including hexagons. And there's a link to a very good tutorial, a document like explaining step by step how to do this. There's also, you can also use density analysis that creates grid of different types, aggregates the points and applies its style to them automatically. So it makes things even easier than the other approach. So that's one option. Then we have other options that you can try using QGIS. You can map OD connections. That's your option B. And then we have option C, that is creating a cartogram. So you can choose one of these options, and create your map. And the submission deadline, because we were a bit late with releasing the materials, you have a bit more time until end of next Wednesday to submit. As usual, you can submit a single PDF and include your map there. And no need to submit your code or anything else.